Standard light sources emit photons in random directions with varying phases and wavelengths. This lack of coordination creates diffuse illumination that spreads rapidly over distance. In contrast, laser systems produce highly ordered electromagnetic radiation through controlled atomic transitions. Understanding this distinction requires examining the specific quantum mechanical processes governing photon generation. After that first surprise, we can slow down and trace the mechanism behind what makes laser light different from normal light. From the first physical step, so the effect stops feeling mysterious and starts feeling engineered. Light is fundamentally an electromagnetic wave that propagates through space as oscillating electric and magnetic fields. In everyday sources like incandescent bulbs, photons are emitted randomly in direction, phase, and wavelength due to thermal agitation of atoms. This creates what we call incoherent light, where the waves overlap chaotically without synchronization. By contrast, laser diodes produce coherent light through stimulated emission that aligns photon phases and directions precisely. Imagine comparing a crowd shouting different words versus an army marching in perfect step. The difference lies in order rather than energy output. Understanding this distinction between thermal randomness and optical coherence sets the stage for examining how atoms generate photons at the quantum level. We will now examine how individual atoms release photons through spontaneous emission processes that differ fundamentally from stimulated laser generation. Pause 0.8 Standard light sources like incandescent bulbs operate through a process called spontaneous emission, where photons are released without external coordination. In this mechanism, electrons within atoms absorb thermal energy and jump to higher, unstable quantum states before randomly returning to their ground levels. Each electron drop occurs independently of neighboring particles, meaning the emitted photons possess random phases, directions, and frequencies rather than synchronized properties. Consider a crowded room where individuals leave through separate doors at unpredictable times versus an organized queue exiting simultaneously through one main entrance. This lack of temporal coordination results in light waves that interfere destructively over short distances, creating the diffuse illumination we observe from everyday sources. Understanding this inherent randomness establishes why we must introduce specific conditions like population inversion to achieve the coordinated photon release required for laser operation. Pause 0.8 In a typical material at room temperature, atoms overwhelmingly occupy their lowest energy state known as the ground level. This natural distribution creates an equilibrium where absorption of photons is far more likely than any form of light amplification. For a laser to function, we must force this system into an unnatural condition called population inversion. In this inverted state, statistical mechanics dictates that significantly more atoms reside in the excited energy level compared to the ground level. Consider a standard thermal source where billions of atoms sit quietly below while only a few are excited versus our target scenario where the majority are primed for release. This reversal is not merely a theoretical curiosity, but a strict prerequisite, because it ensures that stimulated emission events outnumber absorption events within the medium. Without this specific imbalance, any photon attempting to trigger amplification would simply be absorbed by an atom dropping back down rather than creating a cascade of identical photons. Achieving and maintaining this inverted population ratio is therefore the critical gatekeeper for all subsequent light amplification processes. Pause 0.8 To understand laser light, we must examine the specific quantum mechanical event that distinguishes it from ordinary illumination. When an atom exists in a metastable excited state, it possesses excess energy waiting for a trigger to release. An incoming photon with precisely matching frequency approaches this energized atom and interacts directly with its electron cloud. This interaction forces the excited electron to drop to a lower energy level, while releasing a second photon simultaneously. Critically, the newly emitted photon is an exact quantum duplicate of the triggering photon phase, direction, and polarization. Unlike spontaneous emission, where photons scatter randomly, This stimulated process creates coherent light waves moving as one unified beam. This precise duplication mechanism explains why laser beams maintain their intensity over vast distances without spreading out like a flashlight. We now understand the single event that generates identical photons, but we must consider how to amplify this effect for practical use. Pause 0.8 The optical resonator consists of two mirrors positioned at opposite ends of the gain medium to create a closed feedback loop. One mirror reflects nearly 100% of incident photons, while the other allows a small fraction to escape, as the usable laser beam. When an excited atom releases a photon, that particle travels toward either mirror and bounces back into the active region with high probability. This geometric arrangement ensures that photons repeatedly traverse the gain medium, where they stimulate further identical emissions from neighboring atoms. Consider how this differs from normal light sources, where photons travel in random directions and quickly dissipate without amplification. The continuous cycling process selectively reinforces only those wavelengths aligned with the cavity axis, while suppressing off-axis radiation through geometric loss. This sustained feedback mechanism transforms a single spontaneous emission event into a macroscopic coherent wavefront emerging from the partially transparent mirror. Pause 0.8 To understand what makes laser light unique, we must examine how the waves behave over time rather than just their direction. In normal light sources like a light bulb, photons are emitted randomly with no fixed relationship between their wave peaks and troughs. This randomness means that if you were to overlay two separate waveforms from an incandescent source, they would quickly drift out of sync. Laser light operates differently because the emission process forces photons into a synchronized state where their phases remain aligned over extended periods. Imagine comparing two runners on a track. Normal light is like them starting at different times and running at varying speeds, while laser light has them all starting together in perfect step. This temporal coherence allows the wave peaks to maintain fixed relative positions as they propagate through space, creating a stable interference pattern. The mechanism relies on stimulated emission within an optical cavity, where only waves with matching frequencies can sustain themselves over multiple reflections. Pause 0.8 Normal light from a bulb spreads outward in all directions, because each atom emits waves independently. This creates spherical wavefronts that diverge rapidly as they travel through space. In contrast, laser light is confined within an optical cavity where mirrors force photons to bounce back and forth. Only waves traveling perpendicular to the mirror surfaces survive repeated reflections, due to diffraction limits. The surviving waves constructively interfere to form a planar wavefront that exits through one partially reflective mirror. The result is a beam with parallel propagation that maintains its narrow width over significant distances without spreading. For example, a laser pointer can illuminate a spot on the moon while visible from Earth, whereas a flashlight beam would disperse completely. Having established how lasers maintain spatial order, we now examine their temporal properties to understand spectral purity. Pause 0.8 The fundamental distinction between laser light and ordinary illumination lies in the spectral purity of the emitted photons. Normal light sources like incandescent bulbs generate radiation through thermal excitation across a vast array of atomic energy levels. This process results in a broad emission curve, where wavelengths span from infrared to visible ultraviolet simultaneously. In contrast, lasers operate through stimulated emission within a specific resonant cavity that filters out all but one wavelength range. The gain medium only amplifies photons matching the precise energy gap between two defined quantum states of its atoms. Consider a comparison. While sunlight contains every color of the rainbow blended together, laser light isolates a single frequency with extreme precision. This spectral narrowing occurs because the optical cavity reinforces only those waves that constructively interfere after multiple reflections. The result is an output where nearly all photons share identical energy and wavelength characteristics rather than a random distribution. Pause 0.8's laser operation depends on three sequential physical requirements: achieving population inversion, enabling stimulated emission through photon interaction, and maintaining resonance within an optical cavity. These mechanisms collectively produce directional beams with uniform phase relationships across the wavefront.